When Operation Epic Fury launched on February 28, 2026, the world watched as the United States and Israel unleashed one of the most powerful air campaigns in modern history against Iran. The opening salvos came from sea-launched Tomahawk cruise missiles and B-2 Spirit stealth bombers, dropping bunker-penetrating munitions on hardened underground facilities deep inside Iranian territory. F-35 stealth fighters and F-22s swept the airspace clean of any attempted Iranian intercepts. Carrier strike groups repositioned in the Arabian Sea and the Persian Gulf, putting dozens of strike aircraft within range of Iranian targets. In the first hours and days of the campaign, Iran's integrated air defense network was systematically dismantled. Radar sites went dark. Command and control nodes were severed. Surface-to-air missile batteries were struck before they could engage. By March 4th, just 4 days into the campaign, General Dan Caine, chairman of the Joint Chiefs of Staff, was able to stand at a Pentagon podium and declare that the United States had achieved localized air superiority across the southern flank of the Iranian coast. What that declaration meant in practical terms was extraordinary. It meant that American military aircraft could operate over Iranian territory and adjacent waters without facing a meaningful, coordinated air defense response. It meant that the envelope of permissible operations had expanded from the exclusive domain of stealth platforms to include aircraft that in any other scenario against a peer-equipped adversary would have faced catastrophic losses. And it meant that the Army could deploy one of its most capable and lethal weapons systems into a theater that had, just weeks earlier, been one of the most heavily defended airspaces on the planet. The AH-64 Apache attack helicopter had returned to combat, and it was doing something it had never originally been designed to do. By mid-March, United States Central Command confirmed that AH-64 Apaches were operating across Iran's southern flank, hunting targets in and around the Strait of Hormuz. Chairman of the Joint Chiefs of Staff General Dan Caine made it official at a Pentagon briefing on March 19, telling reporters that Apaches had joined the fight on the southern flank. He was direct about what they were doing. American AH-64s were operating in Iraq, striking Iranian-aligned militia groups that had been attacking United States forces and interests since the beginning of the campaign. And allied nation Apaches were operating on the southern flank, engaging one-way attack drones, which had become one of the most persistent and damaging threats Iran could field against its neighbors. The deployment unit on the American side was the 6th Battalion, 17th Air Cavalry Squadron, part of the 4th Infantry Division Combat Aviation Brigade. These were not freshly arrived forces scrambling to adapt to a new theater. They had been deployed to the Middle East since the second half of 2025 under Operation Inherent Resolve, flying AH-64 Delta Variant 14 helicopters and operating in the counter-Iran proxy environment that had defined American rotary wing operations in the region for years. When Epic Fury began, they were already in theater, already familiar with the operational environment, and were integrated into the expanded campaign with the kind of speed that only pre-positioned forces can achieve. The mission profile the Apache was handed in this conflict was not the one that defined its Cold War origins. The AH-64 was designed to kill tanks. It was built, tested, refined, and exported on the premise that its primary reason for existence was to destroy Soviet armored formations trying to push through the Fulda Gap into Western Europe. That mission shaped everything about the aircraft, from the 30mm chain gun optimized to penetrate the top armor of infantry fighting vehicles, to the Hellfire missile designed to defeat the reactive armor of main battle tanks, to the Longbow radar engineered to detect and classify armored targets at range through rain, smoke, and dust. Iran's primary aerial threat in 2026 was not tanks, it was drones. Specifically, it was the Shahed 136, an Iranian-designed one-way attack munition with a delta wing configuration, a small piston engine, and a simple but effective navigation system. The Shahed 136 flies at relatively low speeds, at low altitudes, and it costs a small fraction of what any conventional air defense intercept costs. Iran had manufactured and stockpiled these weapons in enormous quantities, and it had supplied them to proxy forces across the region, including the Houthis in Yemen, Hezbollah in Lebanon, and militia groups in Iraq. When the campaign began, these forces began launching waves of Shaheds at airports, oil facilities, desalination plants, and American military installations throughout the Persian Gulf region. The challenge of defending against mass drone attacks is an economic one as much as a technical one. A Patriot missile battery can engage Shahed drones with PAC-2 or PAC-3 interceptors. But those interceptors cost hundreds of thousands or millions of dollars each, and Iran can produce Shaheds for a few $1,000s apiece. Firing expensive interceptors at cheap drones is a losing proposition at scale. Shorter-range point defense systems can contribute, but they have limited magazines and require positioning close to the assets they are protecting. What was needed was a mobile, persistent, cost-effective interceptor that could engage Shahed drones across a wide geographic area without burning through irreplaceable high-value munitions. The Apache turned out to be a near-perfect answer to that problem. Its Longbow fire control radar, mounted in a distinctive spherical dome above the main rotor mast, can detect, classify, and prioritize airborne targets simultaneously across a wide area. The radar operates at millimeter wave frequencies that cut through atmospheric obscurance and can track the slow, low radar cross-section profile of a Shahed at operationally useful ranges. Once the target is identified, the crew can engage with the 30mm M230 chain gun, which fires at 625 rounds per minute and which costs virtually nothing per shot compared to any guided missile. The gun can be slaved to the gunner's helmet-mounted sighting system, allowing the gunner to look at a target and put rounds on it with a level of intuitive precision that makes the engagement process fast and repeatable. Reporting from the theater indicated that Allied Apache crews were achieving extraordinary engagement rates against Shahed series drones. The Apache's ability to engage multiple targets in a single sortie, reposition rapidly across the patrol area, and operate day and night with full sensor capability made it an ideal defensive platform for the sustained drone suppression mission. The cost calculus was entirely in the defender's favor. A 30mm round destroying a Shahed represents a decisive economic and tactical victory compared to any guided missile intercept. The aircraft could also engage drones at extended range using APKWS, the Advanced Precision Kill Weapon System, a laser guidance kit fitted to standard 70mm Hydra rockets. With APKWS, the Apache can engage aerial targets at ranges of up to 8 kilometers, well outside the threat radius of most Shahed warheads and well beyond the effective range of the chain gun. This extended standoff capability allowed crews to prosecute engagements without entering the lethal radius of targets that might carry fragmentation warheads or explode unpredictably when hit. In Iraq, American Apaches resumed a role that their predecessors had been performing intermittently for years. Qatar, Hezbollah, Harakat al-Nujaba, and affiliated Iranian-backed factions had been attacking the United States Embassy in Baghdad, American military facilities, and positions associated with American interests throughout the country since Operation Epic Fury began. The embassy in Baghdad issued a statement documenting the scope of these attacks, which included drone and missile strikes against the international zone where the embassy is located. For the Army's Apache crews and theater, this was a known, persistent threat that they had operational history with. The Apache provided the ground commander with a fast response, precision strike capability that could reach time-sensitive targets with a short sensor-to-shooter timeline that fixed-wing aircraft operating from more distant bases could not match. Perhaps the most remarkable aspect of the entire Apache deployment was where it operated. Defense Secretary Pete Hegseth confirmed that AH-64s had flown inside Iranian airspace, including over the Strait of Hormuz itself. This statement deserves to be dwelt upon. The Strait of Hormuz is not some remote, poorly defended stretch of water. It is one of the most strategically significant choke points on Earth, through which approximately 20% of the world's oil supply transits daily. Iran had invested heavily in defending it with coastal missile batteries, fast attack boat swarms, mine-laying capability, and shore-based air defense systems. The idea that attack helicopters with a combat radius of several hundred kilometers, aircraft that are slow, loud, and not built for stealth, were flying over this territory without being engaged, tells you precisely how thoroughly the American air campaign had dismantled Iranian defensive capacity in the region. The layered architecture of American electronic warfare and intelligence capability made this possible. The EA-18G Growler, operating from carrier decks in the Persian Gulf and Arabian Sea, provided active jamming and suppression of Iranian radar and communication systems. The E-3 Sentry and E-7 Wedgetail airborne early warning and control platforms maintained continuous situational awareness of the airspace, tracking every emission and every aircraft movement across the theater. Space-based intelligence, surveillance, and reconnaissance assets provided persistent overhead coverage. Cyber operations disrupted Iranian command and control networks at critical moments. The integration of all of these capabilities created corridors of suppressed threat density, through which non-stealth platforms could operate with acceptable risk. The Apache was one of the beneficiaries of this architecture, but it could not have operated as it did without every other element of the joint and coalition force doing its job first. The Strait of Hormuz itself was the focal point of the economic warfare dimension of the conflict. Iran had attempted to use sea mines and fast-attack watercraft to interdict tanker traffic and threaten the oil corridor. General Caine confirmed that American forces had destroyed over 44 Iranian vessels involved in mine-laying operations by March 19. The A-10 Warthog was credited with hunting and killing fast-attack watercraft in the Strait. The Apache, operating in the same contested maritime environment, contributed to this mission by engaging surface threats with Hellfire missiles and providing armed overwatch for naval forces operating in the shallow, confined waters near Iran's coastline, where conventional naval engagements are constrained by geography. What makes the Apache's performance in this campaign even more significant is the context of its institutional history over the preceding years. After the American withdrawal from Afghanistan in 2021, the Apache largely faded from the news cycle. The conflicts that American rotary wing aviation had been prosecuting for 2 decades were winding down, and the platforms associated with them seemed to recede from public consciousness. The Army was simultaneously grappling with modernization questions, debating the future of its attack aviation force structure, and managing the transition of its fleet to the ECHO standard. The Future Attack Reconnaissance Aircraft program was consuming engineering resources and generating debate about whether the Apache's basic design philosophy remained relevant in an era of long-range precision fires and contested airspace. The Iran campaign answered those questions decisively. The Apache is relevant, it is effective, and in the hands of trained crews operating within a properly structured joint force that has done the hard work of establishing air superiority and suppressing enemy defenses, it can operate in environments that would have been considered suicidal for rotary wing aviation in any prior era. To understand why the Apache performs the way it does, you need to understand what the aircraft actually is at the systems level. The AH-64 is not simply a helicopter with weapons attached to it. It is a fully integrated aerial strike platform, and the distinction matters enormously. Every major system on the aircraft is designed to work in concert with every other major system, from the sensor suite that finds and identifies targets, to the fire control computer that manages engagement geometry, to the weapons that deliver effects, to the cockpit displays that present all of this information to 2 crew members who must process it and make lethal decisions in seconds. The physical configuration of the Apache reflects specific doctrinal and operational choices made during its design. The aircraft has a tandem cockpit arrangement, with the co-pilot and gunner seated in the front position and the pilot in the rear position, elevated slightly above and behind the forward crew member. This elevation gives the pilot an unobstructed view over the gunner's head, which matters during nap of the Earth flight when the pilot needs to see terrain features immediately ahead. Both crew members can fly the aircraft and both can operate the weapon systems, giving the crew flexibility to adapt to degraded crew conditions or to divide responsibilities in ways that optimize task loading during complex engagements. The tandem arrangement also narrows the aircraft's frontal profile, which reduces the visual and radar cross-section that a threat system looking head-on at the Apache would see. This is a modest benefit against modern threat systems, but in a design philosophy centered on survivability through every available margin, it reflects the kind of deliberate attention to threat reduction that characterized the entire Apache development program. The airframe is roughly 17 meters in overall length, with a main rotor diameter of approximately 14.5 meters. The stub wings extending from the lower fuselage serve both as attachment points for weapons pylons and as aerodynamic surfaces that offload some of the lift burden from the rotor in forward flight, reducing rotor stress and improving efficiency at cruise speeds. The tail rotor is a conventional 4-blade design mounted on the starboard side of the tail boom, chosen over alternative configurations for its reliability and resistance to combat damage compared to more exotic designs considered during development. Empty weight of the AH-64 Echo is approximately 5,300 kilograms. Maximum takeoff weight is approximately 10,400 kilograms. The difference between those numbers represents the payload and fuel capacity that the aircraft can carry, which is substantial for a platform of its size. In a typical combat configuration carrying 16 Hellfire missiles and a full ammunition load for the chain gun, the Apache is a dense concentration of destructive capability in a relatively compact airframe. The rotor system is central to the Apache's survivability and performance characteristics. The four-blade, fully articulated main rotor uses composite materials that can sustain significant ballistic damage without catastrophic structural failure. Individual rotor blades have been tested against 23mm rounds and have demonstrated the ability to continue generating lift even after sustaining penetrating hits. The rotor hub is similarly hardened, designed to maintain structural integrity after impacts that would destroy less robust designs. This level of ballistic tolerance was a fundamental requirement from the Army's original specification, reflecting the reality that attack helicopters operating at low altitude in a high-threat environment will be hit by ground fire. Power comes from two General Electric T700 turboshaft engines. In the Echo variant, these are the T700-GE701 Delta version, each producing approximately 2,000 shaft horsepower at sea level. The two engines are physically separated within the airframe, mounted on opposite sides of the main gearbox assembly, with armored firewalls between each engine and the fuselage interior. This separation ensures that a single hit cannot destroy both engines simultaneously, and the redundant design means the aircraft can continue flying on one engine if the other is disabled or destroyed. The engines themselves are designed to continue operating for a limited period even after sustaining certain categories of battle damage, providing the crew with enough power to reach a survivable landing zone rather than going down immediately over hostile territory. Performance figures for the Echo variant reflect the balance between payload, range, and agility that the Army required. Top speed is approximately 293 km per hour in level flight. Cruise speed for sustained operations is around 265 km per hour. These are not impressive numbers compared to fixed-wing aircraft, but they are not meant to be. The Apache's performance envelope is optimized for the nap-of-the-earth environment where it operates, where the ability to decelerate rapidly, translate laterally, and transition between hover and forward flight matters far more than top speed. Service ceiling is approximately 6,400 meters, though performance degrades noticeably above 3,000 meters in hot conditions, which was a significant operational constraint during Afghanistan operations. Combat range on internal fuel is roughly 475 kilometers, extendable with external fuel tanks at the cost of weapons payload. Survivability was not an afterthought in the Apache's design. It was a primary requirement that shaped the aircraft from the ground up and influenced decisions across the entire engineering program. The airframe was designed around what the Army called crash-worthiness requirements, which specified the G-load that the aircraft and its crew stations had to survive in an uncontrolled landing or crash scenario. The landing gear, fuselage keel structure, and crew seats all incorporate energy-absorbing elements that decelerate the crew within survivable physiological limits, even in high sink rate impacts. This design philosophy came directly from Vietnam-era data on helicopter crew fatalities, which showed that a significant percentage of deaths resulted from crashes that were survivable if the airframe had not collapsed into the crew. The cockpit armor system uses boron carbide panels, one of the hardest known materials, installed around the crew stations to defeat rounds up to 23 millimeters in size. The crew seats themselves are armored. Critical systems, including hydraulic lines and control runs, are either redundant or routed to minimize the probability that a single hit severs all of them simultaneously. Fuel tanks are self-sealing, meaning they can sustain projectile penetrations and close around the entry and exit holes to prevent fuel loss and reduce the risk of fire. The aircraft uses a nitrogen inerting system in the fuel tanks to reduce the flammability of fuel vapors, addressing one of the most dangerous failure modes in combat helicopter operations. The weapons suite is where the Apache's design philosophy culminates. Every survivability feature, every sensor capability, every communications and navigation system exists to get the crew into position to employ weapons effectively against targets that need to be destroyed. The anchor of the weapon system is the M230 chain gun. The M230 is a single-barrel 30mm automatic cannon using a chain-driven feed mechanism that gives it its name. Unlike Gatling-style rotary cannons that use multiple barrels to achieve high rates of fire, the chain gun achieves its rate of fire through a mechanically elegant design that drives the breech operation with an external motor rather than relying on propellant gas. This means the rate of fire is independent of propellant pressure variations and can be adjusted electronically. The standard rate of fire is 625 rounds per minute, though the system can be set to fire in shorter bursts for ammunition conservation. Maximum ammunition capacity is 1,230 rounds, though operational loads are often configured lower to allow additional weapons on the pylons. What makes the M230 truly dangerous in the Apache's configuration is the integrated helmet and display sighting system, known as IHADSS. This system uses a monocle-style display mounted on the crew member's helmet that presents sensor imagery and flight symbology directly in front of one eye. A helmet position sensing system tracks the orientation of the gunner's head in 3 dimensions. The gun's turret drive system uses this position data to slave the barrel of the M230 to wherever the gunner is looking. The gunner looks at a target, and the gun points at the target. This sounds simple but represents a profound capability in air-to-ground and air-to-air engagements, where engagement windows are measured in seconds, and the ability to acquire and engage without the procedural overhead of a conventional targeting process is a decisive advantage. For drone engagements, where the target may appear in the sensor picture with little warning and may be moving on an intercept course, this instantaneous slaving of gun to gaze is particularly valuable. The stub-wing pylons carry the Apache's heavier weapons. 4 hardpoints arranged 2 per wing can carry a range of stores and mission-configurable loadouts. The most important weapon in the Apache's inventory is the AGM-114 Hellfire missile, a weapon that has been in continuous development and production for over 4 decades, and that has evolved through a family of variants that now bears almost no resemblance to the original design in its guidance and effects capabilities. The original AGM-114 Alpha used semi-active laser homing guidance, meaning the missile used a seeker in its nose to track a laser spot that the Apache or a ground designator was maintaining on the target. This required the laser to stay on target throughout the missile's time of flight, which could be 15 seconds or more for long-range shots. This constraint, known as the laser designation requirement, limited the Apache's tactical flexibility, because it forced the helicopter to maintain a relatively stable targeting attitude while the missile was in flight, increasing its exposure to ground fire. The AGM-114 Bravo and Charlie variants refined the laser guidance system and improved the warhead design. The Delta variant introduced a blast fragmentation warhead variant for use against personnel and soft-skin targets, in addition to the shaped charge anti-armor warhead. But the most significant transformation came with the Romeo variant and the introduction of the Longbow missile system. The AGM-114 Romeo, developed for use with the Longbow fire control radar, uses a millimeter-wave active radar seeker in its nose. After launch, the missile uses this seeker to independently locate and track the designated target based on radar returns, without requiring any further input from the launching aircraft. This is true fire-and-forget capability. The Apache crew can launch the missile, immediately maneuver behind terrain or otherwise break the line of sight to the target, and the missile will continue on its own to find and destroy what it was aimed at. In a high-threat environment where every second of exposure to ground-based air defenses increases the probability of being engaged, fire-and-forget capability is not a convenience. It is a fundamental survivability multiplier. The most unusual and operationally significant recent Hellfire variant is the AGM-114 R9-X. This weapon, which became publicly known through its use in counter-terrorism strikes in the Middle East, eliminates the explosive warhead entirely. In its place, the R9X carries a set of folded blades that deploy immediately before impact. These blades, 6 in number, extend from the body of the missile and spin as the weapon closes on its target, creating a kinetic energy kill mechanism that destroys the target through physical impact rather than explosive blast. The operational rationale is significant. In environments where collateral damage must be minimized, a kinetic weapon that concentrates all of its destructive energy in a small area directly around the point of impact without generating a blast wave or fragmentation pattern, allows strikes that would be impermissible with any conventional explosive warhead. The weapon has been used successfully in strikes against individual targets in vehicles, in buildings, and in populated areas without injuring bystanders in proximity to the target. The Hydra 70 rocket pod completes the Apache's primary weapons options. Each pod, designated the M261, carries 1970mm folding fin aerial rockets. These unguided rockets were a standard rotary wing weapon system for decades, used for area suppression against infantry, light vehicles, and soft targets. The introduction of the APKWS kit transformed the Hydra from an area weapon into a precision-guided munition. The APKWS kit adds a mid-body laser guidance section to the standard rocket, using semi-active laser homing to steer the weapon toward a designated spot. The result is a guided munition with a circular error probable of less than 2 meters at combat ranges, at a cost per round that is orders of magnitude lower than a Hellfire missile. For targets that do not require the penetration capability or the standoff range of a Hellfire, APKWS-equipped Hydra rockets provide a precision strike option that conserves the more expensive missiles for high-value armored or hardened targets. The sensor suite that enables the Apache's targeting capability is built around the Target Acquisition Designation Site and Pilot Night Vision Sensor, universally referred to as TADS PNVS. These are two distinct sensor systems with different functions that work in close coordination. The TADS is mounted in a rotating stabilized turret on the nose of the aircraft and contains several imaging and designating elements. A forward-looking infrared sensor generates thermal imagery for both long-range search and target recognition. A television camera provides high-resolution daylight imagery. A direct-view optic gives the gunner an unmediated visual picture of the scene ahead. A laser rangefinder determines the precise distance to a designated point. And a laser designator illuminates targets for laser-guided weapons, either for the Apache's own Hellfire missiles or to support the deliveries of other aircraft. The entire TADS assembly can be slaved to the gunner's IHADSS helmet so that the sensor suite follows the gunner's line of sight across a wide field of regard in front of and to the sides of the aircraft. The PNVS is a separate forward-looking infrared sensor mounted in a smaller rotating turret above the TADS assembly. Its field of view and scanning range are designed for the pilot's use, providing a continuous thermal imagery feed to the pilot's IHADSS monocle display. The PNVS allows the pilot to fly at low altitude in complete darkness by presenting a navigable thermal picture of the terrain ahead, slaved to the pilot's head movements, so that whatever the pilot looks at, the sensor shows. This capability was genuinely revolutionary when the Apache entered service in the mid-1980s. The ability to fly and fight at night with the same tactical aggressiveness as in daylight gave the Apache a decisive advantage over any adversary without equivalent capability. The modernized Target Acquisition Designation Site and modernized DAIS sensor assembly introduced on the Echo variant represent a substantial improvement over the original TADS in both resolution and processing capability. The MTADS uses a higher resolution infrared sensor and a digital zoom capability that allows the crew to identify targets at ranges significantly greater than was possible with the original system. The improved imagery quality reduces the probability of misidentification and allows the crew to make engagement decisions at greater standoff distances, which translates directly into reduced exposure to ground-based threats. The defining technological feature that separates the Delta and Echo variants from the original Alpha is the Longbow fire control radar system. The radar dome, a sphere approximately half a meter in diameter, sits atop a pylon, mounted above the main rotor mast. This mast mount location is a tactical decision of fundamental importance. By placing the radar above the rotor disc, the Apache can remain completely hidden behind a ridgeline, a tree line, or any other terrain feature that is taller than the aircraft's fuselage, while still exposing the radar dome to scan the threat area ahead. The crew raises the aircraft just enough to bring the radar into the clear, conducts a rapid scan, then descends back behind cover to process the results and plan the engagement. This pop-up tactic is the operational implementation of the Apache's core survivability philosophy: find targets before they find you, and minimize the time you are exposed to counterfire. The Longbow radar operates at millimeter wave frequencies in the W-band. At these frequencies, the radar wavelength is short enough to provide useful resolution against vehicle-sized targets, but long enough to propagate through rain, fog, smoke, and dust that would attrite the performance of optical sensors. The radar can detect ground vehicles, hovering or slow-flying aircraft, and static targets across a sector scan of approximately 90 degrees in azimuth, and process the returns to generate a classified target list in approximately 30 seconds. It can simultaneously track up to 128 contacts and display the 16 highest priority targets to the crew, with symbol overlays indicating target type, range, bearing, and threat classification. In a target-rich environment, this capability allows the Apache crew to rapidly identify the most dangerous and most valuable targets and sequence their engagement without the cognitive overload that manual target prioritization in a confusing visual environment would impose. The radar also enables the fire and forget engagement mode of the Hellfire Romeo. When the crew designates a target using the Longbow radar, the radar's fire control computer calculates a predicted intercept solution and programs the guidance system of the missile before launch. After the missile leaves the rail, the Apache's own radar continues to track both the missile and the target, providing mid-course updates if necessary, but the missile's onboard radar seeker takes over for terminal guidance. The launching aircraft is free to maneuver immediately after firing. One of the less publicized but operationally significant capabilities of the Longbow system is its networked fire control mode, known as Fire and Update. In this mode, one Apache with its Longbow radar active can designate targets and transmit the targeting data over the Army Tactical Data Link to other Apaches in the formation that have their radars switched off. Those aircraft can then launch Longbow-guided Hellfires against targets they have never seen themselves, guided only by the data their teammate transmitted. This capability allows a formation of Apaches to engage a larger number of targets simultaneously than any single aircraft's weapons load would permit, while keeping most of the formation's radar signatures cold and therefore less detectable by threat air defense systems. The communications architecture of the modern Apache has evolved to match the joint data environment of current American military operations. The aircraft carries multiple radios for voice communications across UHF, VHF, and HF bands, allowing it to communicate with Army ground forces, Air Force controllers, naval platforms, and special operations teams simultaneously. The improved data modem provides a digital communications channel compatible with the Army's Force 21 Battle Command Brigade and below system, allowing the aircraft to send and receive digital target reports, situation updates, and mission data over the Army's tactical internet. Link 16 connectivity, introduced on the Echo variant, integrates the Apache into the Joint Tactical Data Link network used by Air Force and Navy aircraft, enabling genuine data-level interoperability with fixed-wing platforms and airborne early warning aircraft that was not possible with earlier generations of Army-specific communications systems. The Apache's ability to serve as a control node for unmanned aerial vehicles represents one of the most significant capability additions of the past decade. The MQ-1C Gray Eagle is the primary unmanned aircraft with which the Apache teams, though the architecture is designed to be compatible with other unmanned systems as capabilities evolve. In the teaming mode, the Apache crew uses a dedicated ground control station capability embedded in the aircraft's digital architecture to fly and control the unmanned aircraft, cueing its sensors, directing its flight path, and receiving its sensor feeds directly on the Apache's cockpit displays. The unmanned aircraft can conduct the initial reconnaissance of a target area, identify and geolocate threats, and even provide the laser designation for Hellfire missiles fired from the Apache, all without the Apache itself ever entering range of the threats it is targeting. This cooperative engagement model dramatically extends the Apache's effective reach and reduces its exposure to counterfire, addressing one of the most persistent vulnerabilities that the platform's combat history has exposed. The AH-64 Echo's open systems avionics architecture is what makes all of these capabilities upgradable over time without requiring a fundamental redesign of the aircraft. The earlier Alpha variant used a largely proprietary, tightly integrated avionics design that made adding new capabilities expensive and time-consuming because any change to one system potentially required changes to everything connected to it. The Echo's architecture uses open standards for hardware interfaces and software communication protocols, allowing new sensors, weapons, or communication systems to be integrated without requiring the replacement of unrelated components. This architectural approach is what allows the Apache to remain operationally relevant through multiple generations of threat evolution, without the kind of wholesale replacement that would otherwise be required. The electronic warfare and self-protection suite on the Echo was also substantially expanded over earlier variants. The aircraft is equipped with a common missile warning system, which uses ultraviolet sensors to detect the launch of surface-to-air and air-to-air missiles directed at the aircraft and automatically triggers the countermeasures dispensing system. A laser warning receiver detects when threat radar or laser rangefinders have illuminated the aircraft, alerting the crew to potential targeting activity. The chaff and flare dispensing system releases decoys that draw away radar-guided or infrared-guided missiles by presenting a more attractive target than the aircraft itself. An electronic warfare management system integrates all of these passive and active defensive measures into a coherent suite that the crew can manage through a single interface rather than individually responding to each warning system. The history of the Apache begins in a specific strategic and historical context that is easy to forget half a century later. In the late 1960s and early 1970s, the United States Army was processing an enormous amount of difficult operational experience from Vietnam and drawing lessons that would shape American military doctrine for decades. One of the central lessons was about helicopters. The A-1 Iroquois, fitted with rocket pods and machine guns to create the armed gunship variant that became the primary rotary-wing fire support platform of the Vietnam War, was a compromise. It was a utility helicopter that had been pressed into the attack role because a dedicated platform did not exist when the war began. It was effective against the light infantry threats of the Vietnamese jungle, but American planners looking at the European theater recognized that it would be wholly inadequate against Soviet armor. The A-1 Cobra entered service in 1967 as the first purpose-built attack helicopter in the American inventory. It was faster than the armed Huey, had a narrower forward profile that reduced its visual signature, and carried a better weapons integration. It performed creditably throughout the remainder of Vietnam and continued to serve in the Marine Corps for decades. But even as it was entering service, its designers and the Army knew that it was a transitional solution rather than the final answer. The Soviet threat it might face in Central Europe was categorically different from the counterinsurgency environment for which it was optimized. The October 1973 Arab-Israeli War provided the most important single input to the advanced attack helicopter program's requirement development. In that conflict, Egyptian and Syrian forces equipped with Soviet-supplied anti-tank guided missiles and man-portable air defense systems inflicted devastating losses on Israeli armor and aircraft in the opening days of the war. The Sagar anti-tank missile, operated by Egyptian infantry, destroyed hundreds of Israeli tanks. Israeli aircraft attempting to operate in the integrated air defense environment that Soviet equipment had created suffered losses at rates that shocked Western analysts. The lessons were stark. Modern air defenses, even those operated by non-superpower forces, could inflict catastrophic losses on aircraft attempting to operate in the low-altitude environment. Any attack helicopter designed to fight Soviet armor in Europe would face an air defense environment orders of magnitude more capable than what Israel had encountered in the Sinai and the Golan Heights. The new aircraft had to be survivable in that environment, which meant it had to be able to engage targets from standoff ranges that kept it outside the engagement envelopes of the most dangerous threats. It had to operate at night when visual air defenses were degraded, and it had to be built to absorb battle damage and keep flying when it inevitably got hit. The Army formally launched the Advanced Attack Helicopter Program in 1972 with a requirements document that codified these lessons into engineering specifications. The aircraft had to operate in all-weather conditions day and night. It had to carry a meaningful anti-armor weapons load. It had to survive hits from weapons likely to be encountered in the Central European threat environment. It had to be capable of operating from improvised forward bases without extensive ground support infrastructure. And it had to be affordable enough to procure in quantities sufficient to make a difference at the operational level, which meant hundreds of aircraft, not dozens. The Army solicited proposals from the American rotary wing industry. Bell Helicopter, the manufacturer of the Huey and the Cobra, submitted a design designated the AH-64. Hughes Helicopters, a division of the Summa Corporation controlled by Howard Hughes, submitted a design designated the AH-64. Both companies built prototype aircraft, and the Army conducted a competitive fly-off evaluation beginning in the summer of 1976. The AH-63 was a capable design, featuring Bell's characteristic two-blade semi-rigid teetering rotor, a design that Bell had refined through decades of production, and that offered simplicity and ease of maintenance. Its proposed gun system used a 20mm weapon, and the overall performance numbers were competitive with the Hughes design in several categories. The AH-64 used a four-blade, fully articulated rotor system that offered better stability, lower vibration, and a different acoustic signature than the Bell teetering rotor. Its proposed gun was the 30mm chain gun, already in development as a separate program, which offered substantially greater destructive potential against armored targets than the 20mm weapon. The design incorporated a wider range of crashworthiness features and placed more explicit emphasis on battle damage tolerance in its engineering trade-offs. The Army selected the Hughes design in December 1976. The official evaluation cited the superior gun system integration, the better crashworthiness characteristics, and the overall performance of the tail rotor design in adverse conditions as key factors. Bell protested the decision, as competing manufacturers routinely do in major defense procurement competitions, but the Army's selection stood and full-scale development proceeded under Hughes helicopters. The full-scale development program from 1976 through the early 1980s was a genuine engineering challenge. The TADS PNVS sensor system, which was the centerpiece of the Apache's night fighting capability and the most technically demanding subsystem in the aircraft, proved particularly difficult to develop. The system had to achieve levels of image quality, stabilization accuracy, and laser ranging performance that pushed the limits of the available technology. Integration with the IHADSS helmet-mounted display required solving human factors problems that had never been addressed in a production military system before. The laser designator had to achieve power levels and pointing accuracy that met the engagement requirements for Hellfire at operational ranges. Testing exposed numerous deficiencies that required engineering solutions. The TADS had significant vibration-induced jitter that degraded image quality until the stabilization system was redesigned. The helmet-mounted display had latency issues that caused disorientation in some crew members until the sensing and processing systems were sped up. The chain gun experienced feed reliability problems under certain temperature and vibration conditions. None of these were unusual for a development program of this complexity and ambition, but each required time and money to resolve, contributing to the cost growth and schedule delays that attracted congressional scrutiny throughout the development program. The cost and schedule challenges of the Apache program were significant enough to generate serious congressional pressure at multiple points during the development and early production phases. The original cost per aircraft estimates proved optimistic as the complexity of the avionics integration became apparent. Congressional hearings examined the program's management and cost trajectory on multiple occasions during the late 1970s and early 1980s. The Army defended the program by pointing to the uniqueness of the capability it was buying, arguing that no cheaper approach could achieve the night-fighting, all-weather standoff engagement capability that the strategic threat demanded. The program survived, but the scrutiny it endured shaped how the Army managed the production contract and how it communicated the program's value to oversight bodies. The first production AH-64 Alpha completed its first flight in January 1984 at Hughes Helicopters facility in Mesa, Arizona. The Army accepted its first production aircraft that same month, and initial operational capability was achieved at Fort Hood, Texas, with the 6th Cavalry Brigade, which served as the first operational Apache unit and the organization responsible for developing the tactics, techniques, and procedures that would guide Apache employment doctrine. In 1984, while the Apache was just entering production, the corporate landscape that produced it changed significantly. McDonnell Douglas, the major aerospace and defense contractor based in St. Louis, acquired Hughes Helicopters from the Summa Corporation for approximately $500 million. The Apache program continued without interruption under the new ownership, and Mesa, Arizona remained the production center. McDonnell Douglas continued producing Alphas and began development work on the Delta variant. When McDonnell Douglas itself merged with Boeing in 1997 in what was at the time the largest merger in American aerospace history, the Apache became a Boeing product, and the Boeing Apache helicopter program in Mesa has remained the center of the platform's production and upgrade work ever since. The Apache's first test of combat came in December 1989 during Operation Just Cause, the United States military intervention in Panama to remove Manuel Noriega from power. A small contingent of Apaches supported the initial assault, using Hellfire missiles to strike Panamanian Defense Forces targets in the opening hours of the operation. The engagements were limited in scope and scale compared to what would follow, but the aircraft performed well, and the crews gained the first operational experience of translating years of training and doctrine into live combat employment. The validation that established the Apache's reputation beyond any doubt came 2 years later. Operation Desert Storm, the coalition campaign to liberate Kuwait from Iraqi occupation, began on January 17, 1991, and its opening engagement was planned, rehearsed, and executed by Apache crews. Iraqi air defenses were organized in depth, with overlapping radar coverage and surface-to-air missile systems providing protection for the entire country. Any strike package entering Iraqi airspace would be detected and engaged unless the radar network could be disrupted first. Coalition planners identified 2 early warning radar sites in western Iraq that formed the critical gap through which the initial wave of strike aircraft would need to pass. Destroying both sites simultaneously, at a precise moment, would open a radar dark corridor. The problem was that any aircraft approaching to destroy them would itself be detected by the radar it was trying to destroy, alerting the entire Iraqi network and eliminating the element of surprise. The solution was to approach from the ground level below the radar horizon. Helicopters could do that. Fixed-wing aircraft could not at the approach speeds required to get into weapons range before detection. 8 AH-64 Apaches from the 1st Battalion, 101st Aviation Regiment, were selected for the mission. They flew for hours in complete darkness across the Saudi desert, navigating with GPS and terrain-following techniques, guided to their release points by MH-53 Pave-Low Special Operations helicopters that had better navigation systems. Special Forces teams on the ground verified the target sites. At 2:38 in the morning local time, the Apaches fired simultaneously. Hellfire missiles destroyed both radar sites within 90 seconds. The gap was open. Within minutes, the first coalition strike aircraft crossed into Iraq undetected, and the air war that would reshape the Middle East had begun. Throughout the 100-hour ground campaign that followed the opening air offensive, Apache crews hunted Iraqi armored vehicles with a systematic lethality that the Iraqis had no answer to. Flying at night with PNVS providing full sensor picture, using TADS to identify and designate targets at ranges Iraqi night vision equipment could not match, the Apaches engaged Iraqi tanks, armored personnel carriers, artillery pieces, and command vehicles with Hellfire missiles and chain gunfire. The thermal signature of armored vehicle engines is clearly visible through forward-looking infrared sensors, even when the vehicles are dispersed and camouflaged. Iraqi crews who believed they were concealed in the darkness found themselves taking Hellfire hits from aircraft they had never seen, never heard in time to react, and had no means to counter. It was a one-sided engagement that validated every design requirement the Army had written into the Advanced Attack Helicopter Program specification. By the end of Desert Storm, Apache crews had destroyed hundreds of armored vehicles, numerous artillery systems, and significant quantities of radar and command infrastructure. The platform's reliability in the demanding heat and dust of the Arabian desert had been substantially better than skeptics had predicted. The sensors worked, the weapons worked. The crews' training had prepared them for the tactical environment they found. Desert Storm made the Apache's reputation as the most lethal attack helicopter in the world, and that reputation has been sustained by every major campaign in which the aircraft has participated since. Development of the AH-64 Delta variant, the Longbow Apache, began formally in the late 1980s, while the Alpha was still in peak production. The Army had recognized early in the Alpha's development that the TADS PNVS sensor suite, while revolutionary for its era, would eventually be surpassed by advances in radar technology, and that a radar-cued engagement capability would be essential in the European threat environment, where atmospheric obscurance, smoke, and the sheer density of potential targets could overwhelm the optical sensor approach. The Longbow fire control radar was developed as a joint program between Lockheed Martin and Northrop Grumman, with Boeing responsible for integrating it into the modified airframe. The Delta also introduced the radio frequency-guided Hellfire Romeo missile, which used the Longbow radar's millimeter-wave data link for mid-course guidance, and its own radar seeker for terminal homing. The full Longbow system, comprising the radar, the missile, the associated fire control computer upgrades, and the improved cockpit displays needed to manage the additional information flow, represented a quantum advance in the Apache's engagement capability. An AH-64 Delta could engage armored targets that an Alpha could not even detect under certain weather and obscurant conditions, and it could do so while remaining entirely behind cover during the radar scan phase of the engagement sequence. The Delta entered service in the mid-1990s and was incorporated into the Army's fleet through a combination of new production and remanufacture of existing Alpha airframes. The transition to Delta standard was accompanied by a comprehensive update to Apache tactics and doctrine that took full advantage of the networked fire control capability. The 1990s also brought the Apache's first post-Cold War operational deployments. In Somalia, Apaches supported operations during the humanitarian intervention and subsequent security missions, operating in the complex urban environment of Mogadishu that was categorically different from the European armor engagement scenario the aircraft had been designed for. In the Balkans, Apaches were deployed to Albania in support of operations over Kosovo, though the political and operational constraints of that conflict limited their actual combat employment. These deployments provided valuable experience in operating the platform in complex political environments with restrictive rules of engagement, experience that would prove directly relevant to the much larger and more demanding deployments that followed. Operation Enduring Freedom, launched in October 2001 in response to the September 11th attacks, brought Apaches into their most sustained combat deployment since Desert Storm. Afghanistan presented a fundamentally different operational environment. The country's average elevation is considerable, with most populated areas sitting above 1,500 meters and many operational areas above 3,000 meters. At these altitudes, helicopter performance degrades significantly. The density altitude, which accounts for both actual altitude and temperature, can reduce a helicopter's payload capacity and climb performance to levels that require careful mission planning and may preclude operations that would be straightforward at sea level. The threat environment was also radically different. There were no Soviet tank formations to engage with Longbow-guided Hellfires. The enemy was dispersed infantry, using small arms, rocket-propelled grenades, and improvised explosive devices, operating from civilian areas and exploiting the terrain in ways that conventional military doctrine had not fully prepared American forces to counter. The Longbow radar, optimized to detect and classify armored vehicles, provided limited advantage against dismounted fighters without vehicles. The TAD's PNVS thermal sensors remained valuable for detecting personnel and vehicles, but the identification problem, distinguishing combatants from civilians in complex terrain, was often more challenging than the detection problem. Despite these challenges, Apache crews in Afghanistan performed essential missions throughout the conflict. They provided close air support to ground forces in contact, flying at low altitude and mountain terrain to engage enemy positions that were suppressing or flanking American and coalition troops. They conducted armed reconnaissance, searching routes and objective areas ahead of ground operations. They performed battle damage assessment following strikes by other platforms. They provided overwatch for special operations raids, ready to engage reinforcing enemy forces, or to suppress fire while personnel were extracted. The direct support relationship between Apache crews and the infantry units they covered was one of the defining partnerships of the Afghanistan War, and it saved lives and engagements throughout the country. The aircraft also sustained combat damage at rates that prompted engineering responses. Small arms fire, which the airframe was designed to survive, was a constant hazard at the low altitudes and slow speeds required for close support. Rocket-propelled grenades, particularly when fired from elevated terrain that allowed shots into the less armored underside or tail of the aircraft, caused serious damage on multiple occasions. The survivability systems generally performed as designed. Crews returned with battle damage that would have destroyed less robust platforms, but the operational experience generated a stream of improvement recommendations that were fed back into the upgrade and modification programs and incorporated into subsequent production and remanufacture work. Operation Iraqi Freedom brought the Apache back to a near-peer armored threat environment and delivered a painful lesson that reshaped Army deep attack doctrine. The invasion of Iraq began on March 20, 2003. In the opening days, The 3rd Infantry Division's Aviation Brigade was assigned to conduct deep attack missions against the Republican Guard's Medina Division, positioned southwest of Karbala. The Army's deep attack doctrine called for Apache formations to penetrate beyond the forward edge of the battle area and engage armored formations in their assembly areas and logistics trains before they could close with American ground forces. On the night of March 23, a large package of AH-64 Deltas launched from forward operating bases and headed north toward the Medina Division's positions. The Iraqi forces, alerted to the Apache approach through a combination of civilian observers reporting by cell phone and communications intercept, prepared a layered defense using every weapon available from small arms to heavy machine guns to anti-aircraft artillery. They also cut power to local towns to eliminate background illumination, reducing the visual contrast that the Apache's thermal sensors relied on for target identification in the dark terrain below. The results were catastrophic for the mission. Every single helicopter in the package sustained battle damage from ground fire. The volume of fire was described by surviving crews as a wall of tracers rising from positions across the entire engagement area. One AH-64 was shot down and its crew, Chief Warrant Officers Ronald Young and David Williams, was captured by Iraqi forces and held prisoner until the fall of Baghdad. The remainder of the package broke off the engagement and returned to base, several aircraft barely making it back with extensive damage. The Karbala engagement did not represent a failure of the Apache as a weapon system. The aircraft's survivability features performed as designed, allowing most crews to bring their aircraft home despite taking fire that would have destroyed a less robust platform. What it represented was a failure of the intelligence and planning process that had not accurately assessed Iraqi defensive preparations, and a failure of the suppression of enemy air defenses architecture that had not cleared the engagement area of the specific ground-based air defense threat that materialized. The Apache, for all its capability, requires a certain operational environment to be effective in the deep attack role. When that environment is not established, when the enemy is alerted and prepared, and the electromagnetic and physical suppression work has not been done, even the world's most capable attack helicopter is vulnerable. The Army internalized this lesson comprehensively. Deep attack doctrine was revised to place far greater emphasis on joint integration, requiring fixed-wing suppression of enemy air defenses, electronic warfare support, and more rigorous pre-mission intelligence assessment before Apache formations were committed to deep attack missions. The revision was not an abandonment of the deep attack concept. It was an acknowledgement that the concept required a more thorough enabling package than the Army had consistently applied in the opening phase of Iraqi freedom. In the years following the deep attack lessons, the Apache continued to serve extensively in Iraq in its direct support and armed reconnaissance roles, where it performed consistently well against the counterinsurgency and sectarian violence threats that dominated the mid-decade period. American Apaches flew thousands of combat hours over Baghdad, Mosul, Ramadi, and Fallujah, providing persistent armed presence over the most contested areas of the country. The combination of the Apache's sensor suite and its ability to loiter over an area for extended periods made it a valuable tool for pattern-of-life intelligence development, where crews observed activity over days and weeks to develop an understanding of insurgent movement patterns, logistics routes, and safe house locations. The transition from the Desert Storm-era Alpha Fleet to the Delta and subsequently to the Echo Standard proceeded continuously through the decade, each successive variant bringing improved capability in the sensors, digital architecture, and weapons integration. The Echo variant's development had a transatlantic dimension that is often underappreciated in American accounts. The British Army had been operating the AH-64 Apache, a license-built variant with Rolls-Royce Turbomeca RTM 322 turboshaft engines in place of the American General Electric power plant, since the early 2000s. The British aircraft incorporated several capability modifications requested by the British Army and was built by AgustaWestland under license from Boeing. British Army Air Corps Apaches deployed to Afghanistan and participated in operations in Libya during the 2011 NATO intervention, where they operated from the flight deck of the Royal Navy's HMS Ocean and demonstrated the platform's capability for naval expeditionary employment. British operational experience contributed to the knowledge base that informed the Echo variant's development, and several British modifications were incorporated or influenced the American Echo design. Boeing delivered the first production AH-64 Echo to the United States Army in 2012. The remanufacture program, which converted existing Delta airframes to Echo standard rather than simply buying all new aircraft, was designed to preserve the substantial investment already made in the existing fleet while bringing the entire operational inventory to the current capability standard. Remanufacturing an Apache to Echo standard involves replacing the cockpit displays, avionics computers, communication systems, rotor blades, and numerous smaller components while retaining the core airframe structure, gearbox, and certain other major assemblies. The Block 3 upgrade package, which entered production concurrently with the Echo remanufacture program, introduced the composite wide-chord rotor blades that are one of the most visible external differences between a Block 3 Echo and earlier variants. These blades, with a wider chord than the original design and a more complex airfoil profile optimized using computational fluid dynamics tools unavailable to the original designers, reduce vibration, improve aerodynamic efficiency, and provide a meaningful increase in payload range performance that is most significant at high altitude and high temperature. In the hot desert environments where the Apache most frequently operates, even modest performance improvements in the hover and low-speed regime have direct operational significance for mission planning and weapons loading decisions. Block 3 also introduced the Joint Air-to-Ground Missile as a certified weapon for the Apache. The JAGM uses a triple-mode seeker that can use millimeter-wave radar, semi-active laser, or uncooled imaging infrared guidance, selectable by the crew based on target type and engagement geometry. Against a vehicle in an open area, the radar mode offers fire-and-forget simplicity. Against a target requiring precise placement of the warhead, laser mode provides exact control. Against targets in cluttered environments where radar returns may be ambiguous, imaging infrared provides a thermal picture that the seeker uses to identify and home on the target. The JAGM's multi-mode architecture reduces the vulnerability to single-mode countermeasures that affects any weapon relying exclusively on a single guidance approach. The most recent development thread for the Apache involves integration with unmanned systems at a level far beyond the early teaming experiments. The Army's Future Attack Reconnaissance Aircraft program, intended to develop a successor to the O-58 Kiowa Warrior in the scout and armed reconnaissance role, was canceled in 2024, redirecting attention to upgraded Apaches and new unmanned platforms. Rather than risking a manned reconnaissance aircraft over contested areas, the concept calls for unmanned aircraft to conduct the initial reconnaissance and target development, while the Apache, with its more capable sensor suite and weapons load, remains at standoff until a target is developed sufficiently for engagement. The Army has conducted multiple exercises demonstrating that a single Apache crew can effectively command and control multiple simultaneously airborne Gray Eagle unmanned aircraft, integrating their sensor feeds into the Apache's own displays and directing their flight paths to develop the operational picture across a wide area. The cognitive demands of this teaming role are significant, and the crew training and human factors implications are still being refined in exercises and experiments. But the basic technical architecture is proven, and the operational logic is compelling in a threat environment where early exposure to advanced air defenses is the primary constraint on rotary wing employment. The export record of the AH-64 is a dimension of its history that directly shaped the Iran campaign of 2026. Egypt received Apaches beginning in the early 1990s and has operated them through multiple variants. Israel has been one of the most operationally active Apache users in the world, employing the aircraft extensively in combat operations in Gaza and Lebanon, and developing specialized tactics and modifications based on operational experience that has influenced the broader Apache community. The Netherlands, Greece, and the United Kingdom brought European perspectives on the platform into its development community. Japan, South Korea, and Singapore brought the Apache into the Pacific theater. The Gulf Cooperation Council nations represent the most operationally significant recent export cluster in the context of the current campaign. Saudi Arabia operates a substantial fleet of Apaches, including Echo variants. The United Arab Emirates operates approximately 30 AH-64 Deltas. Qatar operates approximately 24 aircraft. These fleets were not purchased simply as prestige items. They were integrated into the air forces of nations that understood the threat environment of the Persian Gulf and saw the Apache as a critical capability gap filler for low-altitude strike and armed reconnaissance in the complex terrain and maritime environment of the region. When Epic Fury began and the drone threat from Iranian proxies materialized at scale, these fleets were immediately relevant. Gulf nation Apache crews had been training for years on the platform, had developed their own institutional knowledge of the Iranian drone threat from previous engagement experience, and were positioned across the theater in bases that placed them directly in the path of Shahed attack corridors. Their contribution to the drone suppression mission was not a fortunate coincidence. It was the dividend of decades of investment in interoperability, common platforms, and integration into the American-led security architecture of the Persian Gulf. General Caine's comment that Allied nations were using Apaches to handle one-way attack drones reflected a coordinated, multinational effort that the Apache's broad export base made possible. An American Apache crew and a Saudi Apache crew can share targeting data, coordinate patrol sectors, and execute integrated engagements using the same systems, the same tactics, and fundamentally the same training foundation. That operational interoperability is a strategic asset that the export program created and the Iran campaign activated. As of early April 2026, the Apache continues to operate across the Epic Fury area of responsibility. The operational picture has evolved since the opening weeks of the campaign. Iranian conventional air defense capability over the southern flank has been degraded to a level that allowed even low-performance platforms to operate without facing coordinated surface-to-air missile engagement. The militia threat in Iraq continues, though the sustained pressure from Apache strikes and other American and coalition forces has degraded the most capable and active militia elements. The drone threat from Shahed series munitions persists because Iran has enormous stockpiles of these weapons and continues to supply them to proxy forces across the region, but the Apache-led counter-drone effort has established patterns and procedures that significantly reduce the probability of successful Shahed strikes against defended targets. The campaign has also forced adaptation in Apache crew training and doctrine at a pace that peacetime development cycles cannot match. The drone intercept mission profile, which before this conflict was a training exercise scenario rather than a core operational mission, has been refined through hundreds of actual engagements. Crews have developed engagement geometries, altitude and speed profiles, and sensor-to-gun handoff procedures specifically optimized for the Shahed 136 threat. The lessons from these engagements are being documented and fed back into training programs and doctrine updates that will shape how Apache crews prepare for this mission in the future, changing the platform's employment doctrine in real time in a way that only sustained combat experience can. The AH-64 Apache was designed in response to the Soviet threat to Central Europe in the 1970s. Its designers specified an aircraft that would kill tanks at night, survive in a high-threat air defense environment, and operate from austere forward bases close to the front lines. Everything that has been added to the platform in the half-century since that specification was written, the Longbow radar, the digital avionics, the fire-and-forget missiles, the networked fire control, the unmanned teaming capability, has been added to a foundation that those original designers built correctly. That foundation is why the Apache can be handed a mission it was never designed for, drone interception over a hostile nation's coastline in the middle of an active air campaign, and execute that mission effectively within weeks of the campaign beginning. The underlying technology is good enough, the crew training philosophy is thorough enough, and the operational architecture the Joint Force provides is capable enough that the Apache can adapt. It adapted in Somalia, it adapted in Afghanistan, it paid the price for doctrine failures at Karbala, and the Army adapted the doctrine. It evolved through Panama and Desert Storm, and a decade of counterinsurgency into the most continuously battle-tested attack helicopter the world has ever seen. And now it is adapting again, over the Strait of Hormuz, over the southern coast of Iran, in the skies above one of the most strategically important waterways on Earth, flying missions that would have seemed like science fiction to the crews who flew the first production aircraft out of Mesa, Arizona in 1984. Doing it with the same fundamental platform, continuously improved, continuously upgraded, but recognizably the same machine that defeated Iraqi armor in the desert 35 years ago. That adaptability is not accidental. It is the product of a continuous development investment spanning 5 decades. A training culture that produces crews capable of applying a complex system effectively in novel situations, and an institutional willingness to take the lessons of combat seriously and change what needs to be changed. The Boeing AH-64 Apache is